Alright, hi Year 11s, this is Mr. Lim here again, and this is our next video on gases. It's about pressure and flexible gas containers. Alright, so we're going to be learning about all these different definitions and how flexible gas containers act under various conditions. Alright, so let's have a look. What do we got? So pressure is the force exerted by gas particles on the surface of a container. Okay, so that makes sense. It's effectively the gas particles bouncing on the surface of the container, and those bounces exert a force on that container. All right, a higher frequency of collisions lead to a higher pressure, okay, because the more they bounce across it, as well as how hard they hit it, will effectively increase the force that that surface experiences, right, and therefore the pressure. Okay, the total pressure is composed of the partial pressures of all the gases within a sample. Okay, so the idea is that maybe you have more than one type of gas within a sample, and therefore if gas A, let's say oxygen gas, provides 100 units of pressure, which is kilopascals, so 100 kilopascals, and nitrogen provides another 200 kilopascals, then you would have 300 kilopascals in total. All right, so it's effectively just add up all the partial pressures and then the total is that. So each gas will provide a partial pressure and the total pressure is the sum, right? And then partial pressures can be also thought of as a measure of concentration. So if I say that the nitrogen gas is 200 kilopascals and the oxygen gas is 100 kilopascals, then we would say that the concentration of those nitrogen gas particles would be double of the oxygen concentration. All right, but that's just a couple of definitions. Okay, so next, we learn about internal and external pressure. So pressure can be internal or external. So effectively, whether the particles are banging on the inside of the wall of the container or on the outside wall of the container. All right. So in rigid containers, which is not what we're dealing with right now, but we'll deal with later on, these two values can be different. Internal and external pressures can be different. Okay. So the idea is that in a rigid container, the walls don't move, and so therefore these two values will be different. However, in a flexible container, these two values have to be the same. The internal and external pressure have to be the same. Okay, so let's go through the idea of why. Okay, in a flexible container, the walls can move in or out, changing the volume of the container. All right, so here is a wall. Okay, let's call this side the interior and this side the exterior. All right. And the idea is that this particular object here, this thing here can move back or forward. Okay, so it can move forward or back depending on what happens to it. All right, so the wall will move due to the force exerted on by the interior and exterior gases. All right, so say you have a whole bunch of interior gas particles and a whole bunch of exterior gas particles, right? When an interior gas particle goes and bounces off that wall, it's going to move that wall towards the right, and if an external gas particle bounces along it, it will move it towards the left. All right? So if the wall is not moving, however, therefore the internal and the external forces must be equal. So effectively, the same amount of force by the internal gas particles is equal to the external gas forces as well, right? So effectively, they're pushing on that wall the same amount, and therefore the wall is not moving, right? Changing the position of the wall changes the distance that the interior particles have to move to collide with another wall, and thus changes the frequency of collisions with the container walls. Okay, so changing the position of that wall. So that wall, if it moves forwards or backwards, right? Let's go maybe draw this out again. Okay, so let's say we make this wall a little bit further away. Okay, so here was our first wall where it was, and now the wall has moved across that way. All right, so now what you would say that is that, okay, before this one gas particle would have to go all the way here and then bounce all the way back to collide with another wall. So effectively, you would have to move this distance times 2 to go from one side of the wall to the other side of the wall. Or, just the idea is that, probably not even times 2, but it would have to move that far to collide again with another wall, right? But if you move the wall of the container outwards, right, make it go further away, then the amount of distance that it has to travel is now this much. And if it's moving at the same speed, then it will have to travel further for it to hit another wall, and therefore it will take longer, and therefore the frequency of collisions with the container walls will decrease. Okay, so the idea is it has to travel further, and therefore since it has to travel further, it collides less often, and if it collides less often, there will be a decrease in the pressure. Okay, and then finally, the idea is that changing position of the walls changes the volume of the container. So when I move the wall from here to here, I've effectively changed the volume of the container. All right, so this is the idea of flexible containers compared to rigid containers. Rigid containers, obviously, the walls don't move. I mean, the walls can move, but they only move when you make them move, right? But these flexible containers, they will move to make sure that the internal and external forces are equal. All right, so let's go through an example and let's see how that works. Okay, so let's say that the interior pressure was increased. Okay, if the internal pressure was increased, then the interior force would increase. Okay, so here's that wall. Here are all of the interior dots. Here are all the exterior gas particles, right? So if I make the interior force stronger than the exterior force, right? That means that the wall would have a net movement outwards. Does that kind of make sense? All right, so would overpower the external force, and which would make the wall move outwards. The wall moving outwards means that the interior particles have to now move further to collide with a wall, and thus the frequency of collisions will decrease. Okay, so as this wall moves outwards, the green interior particles have to now move further since the wall moved further away. Since the green particles have to move further, they're going to hit the wall less often with less frequency, and therefore the pressure and the frequency of collisions will decrease. Right, now, this wall will continue to move outwards because there's a net overall force outwards until the interior pressure and exterior pressure equalize. Okay, so the idea is that, okay, I've increased the interior pressure somehow, right? It's now overpowering the external pressure. But now that the wall is moving outwards, this amount of interior pressure is going to decrease. So I'm going to lose, I'm going to lose one of those little arrows. And I can't delete that arrow. Stupid arrow. Okay, I'm going to delete one of those arrows this way. Okay, so those arrows will decrease because the wall has moved outwards, right? And therefore they're going to continue to decrease until the wall has moved outwards sufficiently so that the two pressures equalize, right? And now the container will be at a new and larger volume. All right, so that's the idea there. Okay, so that's the idea of what happens with flexible containers. Okay, so you will change a pressure somehow, right? That will change the equality between interior and exterior forces. Okay, that will make the wall move somehow. The wall moving will change the frequency of interior collisions, and then the wall will move until the pressure equalizes and the container will be at a new volume. So let's go through a couple of examples. All right, well, actually, first of all, how can the pressure be changed? Okay, you can change the pressure by changing the temperature, which changes the speed at which the particles move, which then just changes the frequency and the force that the particles collide with the wall, and therefore change the pressure. Alternatively, you can change the number of moles of things. So you can kind of pump in more or take out some, and that will change the frequency of collisions, right? But the idea stands that interior pressure has to equal exterior pressure. So let's go through a couple of examples. Number one, let's go through a balloon put in liquid nitrogen. Okay, so here's a balloon. All right, it has a couple of interior particles. Okay, and let's say that the interior pressure is equal to 100 kilopascals. Okay, that means that the exterior pressure has to equal to 100 kilopascals as well, because the walls are not moving. This is just a normal balloon before I do anything to it. Now, I drop this balloon into some liquid nitrogen, which is very cold. Okay, and what will happen is that the temperature of the interior particles will decrease. Okay, so the temperature decreases of the interior particles when I dip it inside the liquid nitrogen. So when the temperature of the interior particles decreases, what will happen to the frequency of collisions? Okay, well actually no, first of all I should go through the idea that decreasing the temperature decreases the speed and force of interior particles because they move slower. Okay, which will decrease the frequency of collisions on internal surface. Okay, so the interior pressure decreases. We'll maybe go down to 50. Okay, if now I have a imbalance between the internal and external pressure, I'm going to, so what will happen is that now the external pressure is greater than the interior pressure, right? Actually, I should say that this leads to a decrease in pressure and interior pressure. Okay, so now the exterior pressure is greater than the interior pressure. Now the wall moves inward. And effectively, the volume decreases. Now, with the wall moving inward, that means that, well, I guess I'll just shift down a bit here. The wall moving inward means that the frequency of collisions will increase. So the frequency of collisions will start to increase because the wall has moved inwards and there's less space for those particles. All right? So as the balloon gets smaller, right, now the balloon is smaller, now the same amount of particles are kind of jammed into a much smaller space. The interior pressure will start to go back up again. Oh, you stupid machine. Okay, so that interior pressure is now no longer at 50, but goes back to 100 because the volume is now smaller. All right, and so because the walls are moving inwards, the frequency of collision starts to increase, and then eventually the interior pressure becomes equal to the exterior pressure with the new volume, at new volume. Okay, so that's what happens when you change things about that interior pressure. All right, but that's not the only thing you can do. You can also change the exterior pressure. So let's go through an example of that. And oh, come on, erase. Okay, that not erasing. So let's just go through and do it in a different place. Okay, so we're going to deal with a bubble in the deep ocean. So a bubble in the deep ocean. Let's go through. So here's our ocean, here's our bubble. Okay, so in the deep ocean, you've got increasing pressure as you get deeper. So here we have high pressure and here we have low-ish pressure. Okay, so you have increasing pressure as you get deeper down. So this bubble at the bottom might have an exterior pressure of something like, 300 kilopascals. And since it's a flexible wall container and it's effectively a bubble, right, the interior pressure here must be also 300 kilopascals. All right, but as we go up, the exterior pressure gets smaller. Okay, so all the way back up to back down to 100 kilopascals at the surface. All right, now the interior pressure of this bubble as it goes up has to decrease to match the exterior pressure. Or alternatively, you can think of the idea that the gas particles inside this bubble are pushing outwards onto the water particles, and as the water particles push on it less strongly, the interior gas particles can push against it harder, and the walls start to increase in size. Because the lots of particles that were in here now have to be more spaced out, right? Because the interior pressure now will be equal to the exterior pressure of 200 kilopascals, right? Because the walls got wider, and so therefore there is a decrease in the frequency of collisions with the external wall, right? So here you had a high frequency of collisions, okay? Because the external pressure is getting lower, you have a medium frequency of collisions now because the bubble got bigger. And the bubble got bigger because the interior pressure or the exterior pressure got lower, and so the internal pressure didn't have to push against it so hard. All right. And then finally, when you get to the surface, it gets to a much bigger, right? And so therefore, the internal pressure only has to equal the external pressure, right? So therefore, the gas bubble can get bigger, and you have a low frequency of collisions at the top because the external pressure got lower, so the internal pressure had to push less hard, right? And therefore, if it's pushing less hard, it can just spread out kind of thing. The idea is that it spreads out to push less hard. All right, so that's the idea of changing internal and external pressure for these, the flexible containers. All right, and then we're going to go into what happens when we deal with when you change the volume of these containers rather than changing the particles inside. All right, that's it. Adios.